Hello there, and welcome to the Cozy Curiosity channel. I'm so glad you're here. Maybe you've been thinking about where it all came from, or maybe you just like falling asleep to thoughts about the universe's deepest mysteries. Either way, tonight's journey is for you. There's nothing you need to do now. Just let your body rest, your mind slow down, and your thoughts drift. Because tonight, we're exploring the Big Bang, the moment when everything began. Not just stars or planets, but time itself, space itself, and all the matter and energy that would ever exist. We'll move gently from fact to fact, learning about the universe's first moments, its expansion, the formation of atoms, and the light that still echoes from those ancient times. Some things may surprise you. Others may stay with you like a quiet thought at the edge of sleep. And if these calm explorations help you rest, feel free to like and subscribe. It helps others find their way here too. Now, if you're ready, let's begin. The Big Bang wasn't an explosion in space, but an expansion of space itself. When most people hear the term Big Bang, they imagine some kind of massive explosion, like a bomb going off in an empty room. But that's not quite right. The Big Bang wasn't an explosion that happened at a particular point in space. Instead, it was the beginning of space itself. Before the Big Bang, there was no place for an explosion to occur. Space, time, matter, and energy all emerged together in that first instant. As the universe expanded, it wasn't expanding into anything. Space itself was stretching, carrying galaxies and matter along with it. This is a subtle but crucial distinction. The universe didn't explode outward from a center. Rather, every point in space began moving away from every other point, like dots on a balloon being inflated. There is no center to this expansion, no edge we could travel to. Everywhere in the universe was once the same point, and now everywhere is expanding equally. The universe began approximately 13.8 billion years ago. Through careful measurements of the cosmic microwave background radiation, the expansion rate of the universe, and the ages of the oldest stars, scientists have determined that the Big Bang occurred roughly 13.8 billion years ago. This number isn't exact, and different measurement methods sometimes yield slightly different results, creating what astronomers call tension in cosmology. But the general time frame is well established. To put this in perspective, Earth formed about 4.5 billion years ago, so the universe is roughly 3 times older than our planet. Humans have existed for only a tiny fraction of cosmic history, about 200,000 years, which is less than 0.02% of the universe's total age. Everything we see around us, every star, every galaxy, every atom in our bodies, has a history that stretches back to that singular moment, 13.8 billion years ago, when time itself began ticking forward. In the first fraction of a second, the universe was unimaginably hot and dense. The earliest moments of the universe were extreme, beyond anything we can easily comprehend. In the first trillionth of a second after the Big Bang, temperatures exceeded 10 trillion degrees Celsius. At these temperatures, even atoms couldn't exist. Matter as we know, it couldn't form. Instead, the universe was filled with a seething soup of fundamental particles, quarks and gluons, all moving at incredible speeds, colliding and transforming. The density was equally staggering, with all the matter and energy that would eventually form billions of galaxies, compressed into a space smaller than a single atom. These conditions were so extreme that the normal laws of physics as we understand them may not have fully applied. Gravity, electromagnetism, and nuclear forces might have been unified in ways we're still trying to understand. It was a universe of pure energy, radiating brilliantly, existing in a state far removed from the cold, dark cosmos we inhabit today. The Big Bang Theory was first proposed by Georges Lemaitre in 1927. While many scientists contributed to our understanding of the universe's origin, the Belgian priest and physicist Georges Lemaitre was the first to formally propose what would become the Big Bang Theory. In 1927, he suggested that the universe began from what he called a primeval atom, or cosmic egg, which exploded and expanded to create everything we see. At the time, this idea was radical and met with skepticism. Even Albert Einstein, who had developed the theory of general relativity that made such ideas possible, initially dismissed Lemaitre's proposal. Einstein preferred the idea of a static, eternal universe. However, as more evidence accumulated, particularly Edwin Hubble's observations that galaxies were moving away from each other, scientists began to take Lemaitre's ideas seriously. Today, the Big Bang Theory is the cornerstone of modern cosmology, supported by multiple lines of evidence and refined by decades of careful observation and theoretical work. The term Big Bang was originally meant as a criticism. Ironically, the name we use for the universe's beginning wasn't coined by someone who believed in the theory. In 1949, astronomer Fred Hoyle, who favored an alternative, steady-state model of the universe, used the term Big Bang during a BBC radio broadcast. He intended it as a dismissive, almost mocking description, emphasizing what he saw as the absurdity of the idea that the universe had a sudden beginning. Despite Hoyle's skepticism, the name stuck. It was catchy, memorable, and easy for the public to grasp. Over time, as evidence for the theory mounted, the term Big Bang became the accepted scientific terminology. Hoyle himself never fully accepted the Big Bang Theory, even as the scientific community embraced it. Today, scientists sometimes wish they had a more dignified name for this profound event, but the term has become so embedded in our culture that it's unlikely to change. The Big Bang, despite its casual origins, remains the name for the most significant moment in cosmic history. During the first second, the four fundamental forces separated from each other. In the earliest moments of the universe, the forces that govern all interactions, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. As the universe expanded and cooled, these forces began to separate in a process called symmetry breaking. First, gravity split off, becoming distinct when the universe was about 10 to the minus 43 seconds old, a time known as the Planck epoch. Next, the strong nuclear force separated, followed by the electromagnetic and weak forces splitting apart. Each separation released enormous amounts of energy and fundamentally changed how particles could interact. This sequence of separations determined the structure of the universe. If the forces had separated differently, or if their relative strengths were even slightly different, atoms might not form, stars might not ignite, and life as we know it would be impossible. The universe we inhabit is finely tuned by these early moments of force separation. The universe underwent a period of rapid expansion called inflation. About 10 to the minus 36 seconds after the Big Bang, something extraordinary happened. The universe suddenly expanded exponentially, growing by a factor of at least 10 to the 26 in a fraction of a second. This period, called cosmic inflation, was proposed by physicist Alan Guth in 1980 to explain several puzzles about the universe's structure. Before inflation, the universe was much smaller than an atom. Afterward, it had grown to perhaps the size of a grapefruit, though it was still growing and would continue to do so. Inflation solved problems like why the universe appears so uniform in all directions and why it's geometrically flat. It also explains how tiny quantum fluctuations could be stretched to cosmic scales, becoming the seeds of galaxies and large-scale structure. Inflation remains a leading theory, though scientists are still working to understand exactly what caused it and what kind of energy or field drove this incredible expansion. Quarks and gluons formed the first particles in the universe. In the incredibly hot, dense conditions just after the Big Bang, matter didn't exist in the form we recognize today. The universe was filled with a plasma of quarks and gluons, the fundamental building blocks of protons and neutrons. Quarks are elementary particles that come in several types, or flavors, and they interact through the strong nuclear force, which is carried by particles called gluons. At first, the temperature was so high that quarks moved freely, unable to bind together. This state is called a quark-gluon plasma, and it's something scientists have recreated briefly in particle accelerators. As the universe cooled, quarks began to stick together in groups of 3, forming protons and neutrons, the particles that make up atomic nuclei. This transition happened when the universe was about 1/1,000,000th of a second old. From that point on, matter as we know it began to take shape, setting the stage for atoms, stars, and eventually, us. Protons and neutrons formed when the universe was 1 second old. By the time the universe reached the ripe old age of 1 second, it had cooled enough for protons and neutrons to form and remain stable. These particles, made of quarks bound together by the strong force, are the building blocks of atomic nuclei. At this point, the universe was still too hot for these protons and neutrons to combine into larger structures, but they existed as individual particles scattered throughout space. The ratio of protons to neutrons was determined by the temperature and density at this time, and this ratio would later influence how much hydrogen, helium, and other elements formed. In a sense, the universe's chemical composition was set by conditions in the first few seconds. Every atom in your body contains protons and neutrons that have existed since that time, traveling through billions of years of cosmic history to eventually become part of you. The first atomic nuclei formed during Big Bang nucleosynthesis. About 3 minutes after the Big Bang, the universe had cooled to roughly 1 billion degrees Celsius, cool enough for protons and neutrons to stick together and form atomic nuclei. This process, called Big Bang nucleosynthesis, lasted only about 17 minutes. But in that brief window, most of the universe's hydrogen and helium were created. Hydrogen, the simplest element with just 1 proton, was most abundant, making up about 75% of normal matter. Helium, with 2 protons and 2 neutrons, accounted for about 25%. Tiny amounts of lithium and other light elements also formed. Heavier elements like carbon, oxygen, and iron would have to wait billions of years to be forged inside stars. The fact that we observe this specific ratio of hydrogen to helium throughout the universe is one of the key pieces of evidence supporting the Big Bang theory. Those 3 minutes shaped the chemical character of the cosmos. For hundreds of thousands of years, the universe was opaque to light. After nucleosynthesis, the universe was still far too hot for atoms to form. Free electrons scattered photons of light constantly, making the universe opaque, like a thick fog. Light couldn't travel far before being absorbed and re-emitted, bouncing around in an endless dance with charged particles. This period, called the photon epoch, lasted for about 380,000 years. During this time, the universe gradually cooled as it expanded, but it remained a glowing, turbulent plasma. No stars existed yet, no galaxies, no planets, just a hot, dense soup of particles and radiation slowly cooling and stretching. If you could have looked around during this time, which of course you couldn't, since atoms and molecules didn't exist yet, you wouldn't have seen anything. The light was trapped, unable to travel freely through space. It was a universe of light, but one shrouded in its own glow, waiting for the moment when transparency would finally arrive. The cosmic microwave background is the oldest light we can see. When the universe was about 380,000 years old, it finally cooled enough for electrons and protons to combine and form neutral hydrogen atoms. This moment, called recombination, fundamentally changed the universe. With most electrons locked inside atoms, photons were no longer scattered constantly. Light was suddenly free to travel unimpeded through space. The glow from this moment is still visible today as the cosmic microwave background, or CMB, a faint radiation that fills the entire sky. Over billions of years, the expansion of the universe has stretched these photons, shifting them from visible light into microwaves. The CMB is remarkably uniform, with tiny temperature variations of only a few parts in 100,000. These variations reflect small density differences in the early universe, the seeds that would grow into galaxies and galaxy clusters. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB is one of the strongest pieces of evidence for the Big Bang. After recombination, the universe entered the Dark Ages. Once atoms formed and light could travel freely, you might think the universe became bright. But actually, the opposite happened. The universe entered a period known as the Cosmic Dark Ages, lasting several 100 million years. During this time, there were no stars, no galaxies, no sources of new light. The only illumination came from the cooling glow of the Big Bang itself, which faded as the universe expanded. Space was filled with neutral hydrogen gas, drifting slowly, pulled together by gravity into denser and denser clumps. It was a quiet time, a period of patient accumulation. Gas clouds merged, grew, and began to collapse under their own weight. Deep in the hearts of these collapsing clouds, temperatures and pressures slowly rose. The universe was preparing for its next transformation, waiting for the moment when the first stars would ignite and light would return to the cosmos. But for now, darkness reigned, calm and complete. The first stars formed about 100 to 200 million years after the Big Bang. Gradually, the dense clumps of hydrogen and helium gas that had been growing throughout the Dark Ages reached a critical point. When the cores of these clouds became hot and dense enough, nuclear fusion ignited. Hydrogen atoms fused into helium, releasing tremendous amounts of energy. The first stars were born. These earliest stars, called population 3 stars, were very different from stars today. They contained almost no elements heavier than helium, since those hadn't been created yet. This lack of heavy elements allowed them to grow much larger and hotter than modern stars, perhaps 100 or even 1,000 times the mass of our Sun. They burned fiercely and lived fast, exhausting their fuel in just a few million years. When they died, many exploded as supernovae, scattering the first heavy elements into space. These elements would seed the next generation of stars, and eventually, planets and life. The first stars ended the cosmic dark ages, filling the universe with light once more. The universe is still expanding today at an accelerating rate. One of the most profound discoveries in modern cosmology came in 1998, when two teams of astronomers found that the universe's expansion isn't slowing down, as many expected, but is actually speeding up. Distant supernovae appeared dimmer than predicted, indicating they were farther away than they should be if the universe's expansion were constant or slowing. This acceleration suggests that some mysterious force is pushing space apart, a force we now call dark energy. Dark energy makes up about 68% of the total energy content of the universe, yet we don't understand what it is or why it exists. All we know is that it counteracts gravity on cosmic scales, driving galaxies apart ever faster. This means the universe's future is one of increasing isolation. Galaxies will drift farther and farther apart, until eventually, distant galaxies will be racing away faster than light can travel toward us, disappearing from view forever. The universe is still unfolding, still changing, still expanding into an unknown future. Most of the universe is made of dark matter and dark energy, not normal matter. Everything we can see, stars, planets, gas clouds, galaxies, all the atoms that make up the familiar world, accounts for only about 5% of the universe's total mass and energy. The remaining 95% is made of substances we've never directly detected: dark matter and dark energy. Dark matter, making up about 27% of the universe, doesn't emit, absorb, or reflect light, but we know it exists because of its gravitational effects on galaxies and galaxy clusters. It acts as invisible scaffolding, holding structures together and shaping the large-scale distribution of matter. Dark energy, as mentioned, accounts for about 68% and drives the universe's accelerated expansion. We can't see it, touch it, or measure it directly. These components are among the deepest mysteries in science. Despite our advanced telescopes and detectors, the universe is mostly made of things we don't understand. It's a humbling reminder of how much remains to be discovered about the cosmos and our place within it. The Big Bang didn't happen somewhere. It happened everywhere. One common misconception is imagining the Big Bang as an event that occurred at a specific location, with the universe expanding outward from that spot. But space itself emerged from the Big Bang. There was no place where it happened because there was no space before it. Every point in the universe today was part of the initial singularity, the infinitely small, infinitely dense state from which everything emerged. When the universe expanded, it didn't expand into empty space like a balloon inflating in a room. Space itself expanded, stretching the distances between points. So if you could rewind time and watch the universe shrink, you wouldn't see everything collapsing toward a central point. Instead, you'd see every point getting closer to every other point simultaneously. In this sense, the Big Bang happened everywhere at once. We are all, in a very real way, standing at the center of the universe, because every location is equally the origin point of all that exists. The Big Bang created time itself, so there's no before. When we talk about the Big Bang, It's natural to wonder what came before, what caused it, what existed earlier. But these questions may not have answers, at least not in the conventional sense. Time, as far as we know, began with the Big Bang. If time itself started at that moment, then the concept of before has no meaning. It's like asking what's north of the North Pole. There simply isn't anything north of the northernmost point. Similarly, if the Big Bang marks the beginning of time, there can't be a time before it. Some physicists have proposed ideas involving cycles of universes, quantum fluctuations, or higher dimensions where time might operate differently. But these remain speculative. For now, the best answer science can give is that time began with the Big Bang. And asking what came before is asking a question that may be fundamentally unanswerable. It's one of the universe's deepest mysteries, a boundary where language and logic reach their limits. The Big Bang produced nearly equal amounts of matter and antimatter. In the earliest moments of the universe, matter and antimatter were created in nearly equal amounts. For every particle of matter, a corresponding antiparticle was formed. When matter and antimatter meet, they annihilate each other, releasing energy. If the amounts had been exactly equal, they would have completely destroyed each other, leaving a universe filled with radiation, but no atoms, no stars, no planets, and no life. But somehow, there was a tiny imbalance. For every billion antimatter particles, there were 1,000,000,001 matter particles. After all the annihilation events, that one extra particle per billion remained. This tiny excess is the matter that makes up everything in the universe today. Why this imbalance existed is one of the great unsolved problems in physics. It's called the matter-antimatter asymmetry, and understanding it is crucial to explaining why we exist. Somewhere in the laws of physics, there must be a subtle preference for matter over antimatter, but we haven't fully uncovered what it is. The universe was once small enough to fit in your hand. It's hard to imagine, but everything in the observable universe, all the matter and energy that would eventually form 100 billion galaxies, was once compressed into a space smaller than an atom. During the inflationary period, the universe expanded from this subatomic size to perhaps the size of a marble or grapefruit in a fraction of a second. Even after inflation ended, the universe was still extremely compact by today's standards. What we now observe as the visible universe, spanning 93 billion light-years, was once contained in a region far smaller than your hand. This incredible compression meant that every point in space today was once in direct contact with every other point. That's why the universe is so uniform. Distant regions of space that now seem unconnected were once close enough to exchange energy and information. The universe didn't grow from a small object in a larger space. It was, in its entirety, small, and then it grew. Space itself stretched, carrying everything with it. Cosmic microwave background radiation was discovered by accident. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey, trying to reduce background noise in a sensitive radio antenna. No matter what they did, they couldn't eliminate a persistent hiss coming equally from all directions in the sky. They even removed pigeons nesting in the antenna, thinking bird droppings might be the culprit. Nothing worked. The signal remained. Unbeknownst to them, they had stumbled upon one of the most important discoveries in cosmology, the cosmic microwave background radiation. At nearby Princeton University, Physicists had predicted that if the Big Bang theory were correct, there should be a faint afterglow of radiation left over from the early universe. When the two groups learned of each other's work, they realized Penzias and Wilson had found exactly that. The discovery provided strong evidence for the Big Bang and earned them the Nobel Prize in 1978. Sometimes the greatest discoveries come not from looking for something specific, but from paying attention to what's there. The observable universe has a finite size, but the full universe may be infinite. When we talk about the universe, it's important to distinguish between the observable universe and the universe as a whole. The observable universe is the region of space from which light has had time to reach us since the Big Bang, about 13.8 billion years ago. Because light travels at a finite speed and the universe has a finite age, there's a limit to how far we can see. This limit forms a sphere around us, currently about 46.5 billion light years in radius. But the universe beyond that boundary doesn't just stop, it likely continues, perhaps infinitely. We simply can't see it because the light from those distant regions hasn't reached us yet. If the universe is infinite, then our observable patch is just an infinitesimally small piece of a vastly larger whole. We may never know if the universe is truly infinite or if it's finite, but so large that it appears infinite from our perspective. Either way, what we can see is only a fraction of what exists. Gravitational waves from the Big Bang may still ripple through space, just as the Big Bang left behind the cosmic microwave background, a form of electromagnetic radiation. It may have also produced gravitational waves, ripples in the fabric of space-time itself. These primordial gravitational waves would have been generated during the inflationary period, when space was expanding faster than light. Unlike light, gravitational waves can pass through matter almost unimpeded, so these ancient ripples might still be traveling through the universe today, carrying information about the first moments of cosmic time. Detecting them is incredibly difficult because they would be extraordinarily faint, but scientists are working on experiments to find them. If successful, these observations would provide a direct window into the universe's first fractions of a second, a time when the cosmos was far too opaque for light-based astronomy. Primordial gravitational waves could reveal the physics of inflation and perhaps even hint at the conditions that gave rise to the Big Bang itself. It's one of the frontiers of modern cosmology. The universe's geometry appears to be flat. One of the key questions in cosmology is the shape or geometry of the universe. General relativity tells us that the universe could be flat, curved like a sphere, or curved like a saddle. The geometry depends on the total density of matter and energy in the universe. Measurements of the cosmic microwave background have revealed that the universe is remarkably flat, at least within the observable region. In a flat universe, parallel lines remain parallel forever, and the angles of a triangle add up to exactly 180 degrees. This flatness is somewhat surprising because it requires the density of the universe to be very close to a critical value. If the density were even slightly higher or lower, the universe would have a noticeable curvature. Inflation theory offers an explanation. By expanding the universe so rapidly, any initial curvature was stretched out, much like inflating a balloon makes its surface appear flatter. So the universe we observe today is geometrically flat, a vast level expanse extending in all directions. Quantum fluctuations in the early universe became galaxies. In the strange realm of quantum mechanics, even empty space is never truly empty. Tiny fluctuations in energy and density pop in and out of existence constantly. In the earliest moments of the universe, during the period of inflation, these microscopic quantum fluctuations were stretched to enormous sizes. What started as variations smaller than an atom became differences spanning light years. These fluctuations created slightly denser and slightly less dense regions in the early universe. The denser regions had a little more gravitational pull, attracting nearby matter. Over time, these small differences grew. Denser areas became denser still, eventually collapsing under their own gravity to form stars and galaxies. The less dense regions became the vast voids between galaxy clusters. In this way, the largest structures in the universe, spanning hundreds of millions of light years, arose from the tiniest quantum jitters in the fabric of spacetime. It's a profound connection between the very small and the very large, between the quantum and the cosmic. Neutrinos from the Big Bang still fill the universe. Neutrinos are nearly massless, electrically neutral particles that interact very weakly with matter. They're produced in nuclear reactions, like those in the sun's core or in supernova explosions. But some of the neutrinos in the universe date back to the Big Bang itself. About 1 second after the universe began, when it was cool enough for neutrinos to stop interacting with other particles, they streamed freely through space. These cosmic neutrinos, called the cosmic neutrino background, still exist today, though they've cooled to incredibly low temperatures. There are roughly 300 of them in every cubic centimeter of space, passing through everything, including you, without leaving a trace. Detecting these primordial neutrinos is one of the great challenges in physics, as their low energy makes them nearly impossible to observe. But if we could detect them, they would provide another direct glimpse into the universe's first moments, complementing the cosmic microwave background and potentially revealing new secrets about the early cosmos. The temperature of the universe has dropped from trillions of degrees to just a few degrees above absolute zero. At the moment of the Big Bang, the universe was unimaginably hot, with temperatures exceeding 10 trillion degrees. As the universe expanded, it cooled, following a predictable pattern. By the time atoms formed, 380,000 years later, the temperature had dropped to about 3,000 degrees Celsius, roughly the temperature of a star's surface. Today, 13.8 billion years later, the average temperature of the universe is a chilly 2.7 Kelvin, just 2.7 degrees above absolute zero, the coldest possible temperature. This temperature is the remnant heat of the Big Bang, measured through the cosmic microwave background. As the universe continues to expand, it will keep cooling, approaching, but never quite reaching absolute zero. Eventually, trillions of years from now, the universe may become so cold and dilute that even atoms decay, and matter itself becomes a faint memory. But for now, the universe retains a faint warmth, a whisper of its fiery origin. Helium in the universe is evidence for the Big Bang. One of the strongest pieces of evidence supporting the Big Bang theory comes from the abundance of helium in the universe. Astronomers observe that roughly 25% of normal matter in the universe is helium, with most of the rest being hydrogen. This ratio is remarkably consistent, no matter where we look, in distant galaxies, ancient gas clouds, or nearby stars. Stars produce helium through nuclear fusion, but not enough to account for the total amount we see. The only way to explain the observed helium abundance is through Big Bang nuclear synthesis, the process that occurred in the first few minutes of the universe. The temperature, density, and expansion rate during those early moments predicted exactly the ratio of hydrogen to helium we observe today. This match between theory and observation is so precise that it's considered one of the key confirmations of the Big Bang model. The helium in your child's balloon, the helium in a gas giant planet, all of it was created in the universe's first 3 minutes. The Planck epoch was the universe's first moment, and we don't fully understand it. The Planck epoch refers to the very first instant after the Big Bang, from time 0 to about 10 to the minus 43 seconds. During this unimaginably brief period, the universe was so hot, dense, and small that our current theories of physics break down. Quantum mechanics and general relativity, the two pillars of modern physics, each work beautifully in their respective domains, the very small and the very large. But during the Planck epoch, both regimes overlapped. The universe was both incredibly tiny, requiring quantum mechanics, and incredibly dense, requiring general relativity. Unfortunately, these two theories are incompatible with each other. We don't yet have a theory of quantum gravity that can describe what happened during the Planck epoch. This is one of the greatest unsolved problems in physics. Until we develop a unified theory, the very first moment of the universe remains a mystery, a frontier where science reaches its current limits and can only speculate about what might have been. The universe's expansion rate varies depending on where we look. Astronomers have been measuring the universe's expansion rate, called the Hubble constant, using various methods. But recently, they've encountered a puzzling problem. Different measurement techniques give different results. When scientists measure the Hubble constant using the cosmic microwave background, they get one value. When they measure it using nearby supernovae and Cepheid variable stars, they get a higher value. This discrepancy is known as the Hubble tension, and it's one of the biggest mysteries in cosmology today. The difference might seem small, but it's larger than the uncertainties in the measurements, meaning something might be wrong with our understanding of the universe. Perhaps dark energy is changing over time, or maybe there are unknown components of the universe affecting the expansion, or it could indicate a flaw in our measurement methods. Resolving the Hubble tension is critical, as it may reveal new physics or force us to revise fundamental aspects of the Big Bang model. Redshift tells us the universe is expanding. When astronomers observe distant galaxies, they notice something curious. The light from these galaxies is shifted toward the red end of the spectrum. This phenomenon, called redshift, is a result of the Doppler effect, the same effect that makes a siren's pitch drop as it moves away from you. But in the case of galaxies, the redshift isn't because the galaxies themselves are moving through space. Instead, it's because space itself is expanding, stretching the wavelengths of light as it travels toward us. The farther away a galaxy is, the more its light is redshifted, indicating it's receding faster. This relationship, discovered by Edwin Hubble in 1929, provided the first direct evidence that the universe is expanding. By measuring redshift, astronomers can determine not only how fast galaxies are moving away, but also how far away they are, and how the universe's expansion has changed over time. Redshift has become one of the most important tools in cosmology, allowing us to map the universe's history. The Big Bang wasn't silent. It created sound waves. In the first 380,000 years after the Big Bang, the universe was a hot, dense plasma where photons, electrons, and protons interacted constantly. Pressure waves, essentially sound waves, rippled through this plasma, compressing and rarefying matter in rhythmic patterns. These sound waves were driven by the same quantum fluctuations that would eventually form galaxies. The cosmic microwave background preserves a snapshot of these sound waves, frozen at the moment when atoms formed and light could travel freely. By analyzing the patterns of hot and cold spots in the CMB, scientists can determine the notes of these primordial sound waves. This field of study, called cosmic acoustics, has allowed researchers to measure the universe's composition, age, and geometry with incredible precision. The universe rang like a bell in its early moments, and we can still hear the echoes of that sound, encoded in the light from the ancient sky. It's the oldest music in existence. The first galaxies formed about 400 million years after the Big Bang. After the first stars ignited and ended the cosmic dark ages, gravity continued its work, pulling together larger and larger structures. By about 400 million years after the Big Bang, the first galaxies began to form. These early galaxies were much smaller and messier than modern galaxies like the Milky Way. They were irregularly shaped, filled with hot, young stars, and lacked the graceful spiral arms or smooth elliptical forms we see today. These baby galaxies merged and collided frequently, growing larger over time. With each merger, they gained mass, forming new stars from the gas and dust brought together in the collision. The Hubble Space Telescope, and more recently, the James Webb Space Telescope, have peered deep into space and back in time, observing some of these ancient galaxies. They appear as faint smudges of light, but they represent the building blocks of the universe's structure. Over billions of years, these small galaxies would grow into the majestic cosmic cities we observe today. The Big Bang produced all the hydrogen in the universe. Hydrogen is the simplest and most abundant element in the universe, making up about 75% of all normal matter. It consists of just one proton and one electron. Nearly all of this hydrogen was created in the first few seconds after the Big Bang. As the universe cooled from its initial state of quarks and gluons, protons formed, and most of them remained as single hydrogen nuclei. Some hydrogen was later converted into helium and heavier elements in stars, but the vast majority has remained hydrogen since the beginning. The hydrogen in water, the hydrogen in your body, the hydrogen in the sun and in distant gas clouds, all of it dates back to the universe's first moments. It's a direct connection to the Big Bang, a tangible piece of cosmic history. Every time you drink water, you're consuming hydrogen atoms that are as old as time itself, born in the fiery crucible of the universe's origin and traveling through billions of years to eventually sustain your life. Edwin Hubble discovered that galaxies are moving away from us. In the 1920s, astronomer Edwin Hubble made one of the most important discoveries in the history of science. Using the 100-inch Hooker telescope at Mount Wilson Observatory, he measured the distances to several galaxies and their velocities. He found that nearly all galaxies were moving away from us, and the farther away they were, the faster they were receding. This relationship, now called Hubble's law, was the first observational evidence that the universe is expanding. Before this, many scientists, including Albert Einstein, believed the universe was static and eternal. Hubble's discovery changed everything, providing strong support for the Big Bang theory and opening the door to modern cosmology. Hubble didn't just show that galaxies were moving, he revealed that space itself was expanding, carrying galaxies along with it. His work laid the foundation for our current understanding of the universe's origin and evolution. The Hubble Space Telescope, launched in 1990, was named in his honor. The universe's density determines its ultimate fate. One of the most profound questions in cosmology is how the universe will end. The answer depends largely on the universe's density. If the density is higher than a critical value, gravity will eventually halt the expansion and pull everything back together in a big crunch, the reverse of the Big Bang. If the density is lower than the critical value, the universe will expand forever, growing colder and more dilute, ending in a big freeze where stars burn out and entropy reaches its maximum. If the density is exactly at the critical value, the universe is flat and will expand forever, but at a gradually slowing rate. Current observations suggest the universe's density is very close to this critical value. But the discovery of dark energy complicates things. Dark energy is causing the expansion to accelerate, which suggests the universe will expand forever, perhaps ending in a big rip where the acceleration becomes so extreme that even atoms are torn apart. The universe's fate remains uncertain, but it's connected to its beginning in profound ways. There's more energy in empty space than we once thought. One of the strangest discoveries in physics is that empty space isn't truly empty. Even in a perfect vacuum, with no matter or radiation present, space itself contains energy. This is called vacuum energy, or zero-point energy, arising from quantum fluctuations, where virtual particles briefly pop into existence before disappearing. While individual fluctuations are tiny, when you add them up across all of space, the total energy should be enormous. However, observations show that the actual energy density of space, likely related to dark energy, is far smaller than quantum mechanics predicts. In fact, the discrepancy is enormous, off by a factor of 10 to the 120, one of the largest unsolved problems in physics. Despite this puzzle, the energy of empty space has real effects. It's thought to be the source of dark energy, driving the universe's accelerated expansion. The fact that space itself holds energy is a profound insight, hinting that the vacuum is a dynamic, active thing, not just nothingness. The Big Bang didn't create the universe out of nothing, we think. A common question is whether the Big Bang created the universe out of nothing. The answer is subtle and depends on what we mean by nothing. In physics, even a vacuum isn't truly nothing. It's a seething quantum foam of virtual particles and fields. The Big Bang may have arisen from a quantum fluctuation in such a vacuum, or from some pre-existing state we don't yet understand. Some theories suggest the universe emerged from a higher dimensional space, or that it's part of a multiverse where universes are constantly being created. The reality is, we don't know what, if anything, existed before the Big Bang, or whether before even makes sense. The Big Bang marks the beginning of our observable universe, but whether it represents an absolute beginning of all existence remains an open question. What we can say is that the Big Bang was the start of space, time, and matter as we know them, a moment of profound transformation from some prior state into the cosmos we inhabit. Light from the Big Bang is everywhere around us. Right now, as you read this, you are bathed in light from the Big Bang. The cosmic microwave background radiation surrounds us constantly, coming from all directions in the sky. It's invisible to our eyes because it's in the microwave part of the spectrum, but with the right instruments, it can be detected. In fact, about 1% of the static on an old analog television, set tuned between stations, comes from this ancient light. This radiation has been traveling for over 13 billion years, carrying information about the early universe. It's the oldest light we can observe, a direct message from a time when the universe was just beginning to form atoms. The uniformity of this radiation tells us the early universe was remarkably smooth, while the tiny temperature variations reveal the seeds of all future structure. Detecting and mapping the CMB has been one of the great triumphs of modern astronomy, providing a baby picture of the cosmos and confirming many predictions of the Big Bang theory. Baryonic matter is the stuff we're made of, but it's only a small fraction of the universe. When scientists talk about normal or baryonic matter, they mean the protons, neutrons, and electrons that make up atoms, the familiar stuff we interact with every day. This includes stars, planets, gas clouds, and everything we can see and touch. But baryonic matter accounts for only about 5% of the universe's total mass and energy. The rest is dark matter and dark energy, which don't interact with light and remain largely mysterious. Even within the small fraction of baryonic matter, most of it isn't in stars or planets, but in diffuse gas clouds between galaxies. Only a tiny percentage of the universe's matter is concentrated in dense objects like stars, and an even tinier fraction is organized into planets, living organisms, and conscious beings. In a sense, we are made of the universe's rarest form of matter, the kind that can think, wonder, and seek to understand its own origins. It's both humbling and extraordinary. The universe's transparency happened suddenly. The transition from an opaque universe to a transparent one didn't happen gradually over millions of years. It occurred relatively quickly, perhaps within a few tens of thousands of years, a blink of an eye in cosmic terms. Before recombination, photons were constantly scattering off free electrons, making the universe foggy. But as soon as electrons combined with protons to form hydrogen atoms, the scattering stopped almost immediately. Light could suddenly travel vast distances without interruption. This sudden clearing is why the cosmic microwave background appears as a thin shell around us, representing a specific moment in time, rather than a long, drawn-out process. If recombination had been gradual, the CMB would be much more spread out and harder to observe. The abruptness of this transition gave us a clear snapshot of the universe at age 308,000 years, a gift for cosmologists trying to understand the early cosmos. It was like the fog lifting all at once, revealing the landscape beneath. Cosmic inflation explains why the universe looks the same in all directions. One of the puzzles that inflation theory solved is the horizon problem. When we observe the cosmic microwave background, we see that regions of the sky that are on opposite sides of the universe have nearly identical temperatures. This is strange because, according to the standard Big Bang model without inflation, these regions were never in contact with each other. They were too far apart for light to travel between them, so how could they have reached the same temperature? Inflation provides an answer. Before the rapid expansion, the entire observable universe was so small that all its parts were in contact, allowing them to reach thermal equilibrium. Then inflation stretched space by an enormous factor, pushing regions that were once close together to vast distances. So even though these regions appear unconnected today, they share the same properties because they were once part of the same small patch of space. Inflation explains the universe's remarkable uniformity, solving one of the Big Bang theory's greatest challenges. Dark matter played a crucial role in forming galaxies. Without dark matter, the universe would look very different. After the Big Bang, baryonic matter, the normal matter made of protons and neutrons, was moving too fast and spread too thin to collapse efficiently under gravity alone. Dark matter, which doesn't interact with light or normal matter except through gravity, was unaffected by radiation pressure. It began clumping together much earlier, forming gravitational wells that acted like seeds for structure formation. As the universe expanded and cooled, baryonic matter fell into these wells, gathering in the densest regions where dark matter had concentrated. Over time, this led to the formation of the first stars and galaxies. Dark matter's gravitational influence shaped the large-scale structure of the universe, creating the cosmic web, a vast network of filaments and voids that spans the cosmos. Galaxies formed at the intersections of these filaments, where dark matter was most concentrated. In a real sense, dark matter is the invisible skeleton upon which the visible universe is built. The Big Bang may have been preceded by a previous universe. While the standard Big Bang model describes the universe beginning from a singularity, some theoretical physicists have proposed alternative scenarios. One idea is the cyclic model, where the universe goes through endless cycles of expansion and contraction. In this view, the Big Bang wasn't the absolute beginning, but rather a transition point, a bounce from a previous universe that collapsed. Another idea involves eternal inflation, where our universe is just one bubble in a vast multiverse, with new universes constantly being created. There's also the ekpyrotic model, which suggests our universe arose from the collision of higher dimensional membranes. These ideas are highly speculative and remain unproven, but they represent serious attempts to address the question of what, if anything, came before the Big Bang. While we may never know for certain, these theories expand our thinking about the nature of reality and remind us that the universe's origin may be even stranger than we currently imagine. The cosmic microwave background has tiny temperature variations that map the early universe. When the cosmic microwave background was first discovered, it appeared remarkably uniform, with the same temperature everywhere. But with more sensitive instruments, scientists found tiny variations, on the order of a few millionths of a degree. These hot and cold spots aren't random. They correspond to regions of slightly higher and lower density in the early universe. Denser regions appear slightly warmer, less dense regions slightly cooler. These variations are the result of quantum fluctuations during inflation, stretched to cosmic scales. Over billions of years, the denser regions attracted more matter and became the sites where galaxies and galaxy clusters formed. The less dense regions became the voids between structures. By mapping these temperature variations, cosmologists can learn about the universe's composition, age, geometry, and how structure evolved over time. Missions like NASA's COBE, WMAP, and the European Space Agency's Planck satellite have created increasingly detailed maps of the CMB, revealing the universe's history with extraordinary precision. The universe doesn't have an edge or center. In everyday experience, objects have edges and centers. A table has edges you can reach. A ball has a center point. But the universe doesn't work this way. Because the Big Bang happened everywhere simultaneously, every point in space was part of the initial singularity. As space expanded, no particular location became a center. If the universe is infinite, which it might be, then it extends endlessly in all directions with no edge or boundary. If the universe is finite, but curved like the surface of a sphere, you could travel in a straight line and eventually return to your starting point without ever encountering an edge. From our perspective, it appears as if we're at the center because galaxies in all directions are moving away from us. But an observer in any other galaxy would see the same thing. The expansion isn't like an explosion from a central point. It's like dots on the surface of an inflating balloon, all moving apart from each other. There is no preferred location, no edge, no center. The universe is, in a profound sense, everywhere and nowhere. The fine-tuning problem asks why the universe's constants are just right for life. The laws of physics contain several fundamental constants, like the strength of gravity, the charge of the electron, and the mass of the proton. Remarkably, these values fall within a very narrow range that allows for the existence of atoms, stars, planets, and life. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars wouldn't form at all. If the strong nuclear force were a bit different, atoms couldn't hold together. This fine-tuning of the universe's constants has puzzled scientists and philosophers. Is it just luck? Some argue it's evidence for a multiverse, where countless universes exist with different constants, and we happen to live in one where the values allow for our existence. Others suggest it might point to deeper physical principles we don't yet understand, or even to the controversial idea of intelligent design. Regardless of the answer, the fine-tuning problem page reminds us how special and improbable our universe seems to be. The Wilkinson microwave anisotropy probe revolutionized our understanding of the universe. Launched in 2001, the Wilkinson microwave anisotropy probe, or WMAP, was designed to measure the cosmic microwave background with unprecedented accuracy. Over 9 years, it mapped the temperature variations in the CMB across the entire sky, revealing the patterns of hot and cold spots that reflect the early universe's structure. UMAP's data allowed scientists to determine the age of the universe to within 1% accuracy, measure its composition, and confirm that space is geometrically flat. It also provided strong evidence for inflation and mapped the distribution of dark matter. The results from WMAP transformed cosmology from a field full of uncertainties into a precision science. It painted a detailed portrait of the universe at age 380,000 years, showing us what the cosmos looked like long before stars and galaxies formed. WMAP's successor, the Planck satellite, provided even more detailed measurements, but WMAP was the mission that brought the early universe into sharp focus for the first time. Photons outnumber atoms in the universe by 1 billion to 1. When we think about what the universe is made of, we often focus on matter, atoms, stars, and planets. But by sheer numbers, photons dominate. For every atom in the universe, there are about 1 billion photons. Most of these photons are part of the cosmic microwave background, the relic radiation from the Big Bang. This imbalance between photons and atoms tells us something important about the early universe. It reflects the conditions during the first moments when matter and antimatter annihilated, leaving behind a tiny excess of matter and a vast sea of radiation. Over time, as the universe expanded and cooled, the energy of these photons decreased, but their number remained. Today, they form a faint glow filling all of space, a reminder that the universe is fundamentally more radiation than matter. Even though we experience the universe as a material place, filled with solid objects and living things, On the cosmic scale, light reigns supreme. The Big Bang produced only light elements. Heavier ones came later. While the Big Bang nucleosynthesis created hydrogen, helium, and traces of lithium in the first few minutes, all the heavier elements in the periodic table, carbon, nitrogen, oxygen, iron, gold, and so on, were produced much later in the cores of stars. Stars fuse hydrogen into helium, and in more massive stars, helium fuses into carbon, oxygen, and heavier elements. When these massive stars reach the end of their lives, they explode as supernovae, scattering these elements into space. Subsequent generations of stars and planets form from this enriched material. Every atom of carbon in your body, every breath of oxygen you take, every drop of iron in your blood was forged in the heart of a star that lived and died before our solar system formed. We are, quite literally, made of stardust, the remnants of stellar processes that began long after the Big Bang. The universe started simple, with just a few elements, and through the life and death of stars, it grew richer and more complex over billions of years. The universe is about 13.8 billion years old, but the most distant light we see is from objects now 46 billion light-years away. This seems paradoxical. If the universe is 13.8 billion years old, how can we see light from objects now 46 billion light-years away? Shouldn't the farthest we can see be 13.8 billion light-years? The answer lies in the expansion of space. When light from a distant galaxy was emitted, the galaxy was much closer to us. But as the light traveled toward us, the space between us and the galaxy continued to expand, carrying the galaxy farther away. By the time the light reaches us, the galaxy is much farther than it was when the light was emitted. In fact, the farthest objects we can observe, whose light has been traveling for nearly the entire age of the universe, are now about 46 billion light-years away due to this expansion. This means the observable universe has a diameter of about 93 billion light-years, even though it's only 13.8 billion years old. It's one of the strange consequences of living in an expanding universe. The universe's expansion is stretching light itself, making distant galaxies appear redder. As the universe expands, the space between us and distant galaxies increases, stretching the wavelengths of light traveling through that space. This stretching shifts light toward the red end of the spectrum, a phenomenon called cosmological redshift. The farther away a galaxy is, the longer its light has been traveling, and the more space has expanded during that journey, resulting in a greater redshift. Some of the most distant galaxies are so redshifted that their visible light has been stretched into the infrared, making them invisible to optical telescopes, but observable with infrared instruments like the James Webb Space Telescope. This stretching of light is direct evidence of the universe's expansion and provides a way to measure how fast the universe is growing. By studying redshift, astronomers can map the history of cosmic expansion, determine when galaxies formed, and understand how the universe has evolved. It's a tool that turns light into a time machine, revealing the distant past. Every atom in your body is billions of years old. The atoms that make up your body, your skin, your bones, your DNA, are ancient beyond comprehension. The hydrogen atoms in your body were created in the Big Bang roughly 13.8 billion years ago. The carbon, nitrogen, oxygen, and other heavier elements were forged in the cores of stars that lived and died billions of years before our solar system formed. When those stars exploded as supernova, they scattered these elements into space, where they eventually became part of the gas cloud that collapsed to form the sun and planets. Over billions of years, through countless processes and transformations, some of those atoms ended up in you. They've been part of rocks, water, air, plants, animals, and countless other forms before becoming part of your body. And after you die, they'll continue on, joining new forms, new structures, new lives. In this way, you're connected to the entire history of the universe, a temporary arrangement of ancient matter, thinking and breathing and wondering about its origins. The James Webb Space Telescope can see galaxies formed just a few 100 million years after the Big Bang. Launched in 2021, the James Webb Space Telescope is the most powerful infrared telescope ever built. One of its primary missions is to observe the earliest galaxies, formed when the universe was only a few 100 million years old. Because light from these galaxies has been traveling for over 13 billion years, it has been redshifted from visible light into the infrared, where Webb's instruments excel. Early observations from Webb have revealed galaxies that are farther, older, and more luminous than expected, challenging some of our assumptions about how galaxies formed and evolved. These ancient galaxies appear as they were when the universe was just beginning to emerge from the Dark Ages, offering a glimpse into a time when the first large structures were taking shape. By studying these distant objects, scientists hope to understand how the universe transitioned from a smooth, nearly uniform state to the rich, complex cosmos we see today, filled with galaxies, stars, and planets. The universe's age can be measured in multiple independent ways, all giving similar results. One of the strengths of the Big Bang theory is that the universe's age can be determined using several different methods, and they all agree within reasonable margins of error. One method involves measuring the cosmic microwave background and using it to infer the universe's expansion history. Another method looks at the ages of the oldest stars in globular clusters, which can't be older than the universe itself. A third method uses the observed expansion rate, the Hubble constant, to calculate how long the universe has been expanding. Yet another approach examines radioactive decay of elements in ancient rocks and meteorites, providing minimum ages for the solar system, and by extension, the universe. Despite using very different techniques and types of data, all these methods converge on an age of about 13.8 billion years, give or take 100 million. This consistency across independent measurements gives scientists confidence that the Big Bang model is correct and that we understand the universe's history in broad strokes. There's an echo of the Big Bang in the distribution of galaxies across space. The tiny density fluctuations that formed in the early universe, those quantum ripples stretched by inflation, didn't just create the patterns we see in the cosmic microwave background. They also seeded the distribution of galaxies billions of years later. Astronomers have mapped the positions of millions of galaxies and found that they aren't randomly scattered through space. Instead, they form a vast cosmic web, with galaxies concentrated along filaments and sheets, separated by enormous voids. The scale of these structures reflects the sound waves that rippled through the early universe. By measuring the typical distance between galaxy clusters, scientists can detect a standard ruler, a characteristic scale imprinted by the physics of the early universe. This pattern, called the baryon acoustic oscillation, is another echo of the Big Bang. frozen into the architecture of the cosmos. It's a connection between the universe's first moments and the large-scale structure we see today. Spanning billions of light years and billions of years, time tends. The universe may have higher dimensions we cannot perceive. String theory and other advanced theories in physics suggest that the universe might have more than the 3 spatial dimensions we experience. These extra dimensions could be curled up so tightly, compactified at scales far smaller than atoms, that we cannot detect them directly. If these dimensions exist, they could help explain some of the mysteries of the Big Bang and the early universe. For example, inflation might have been driven by processes involving higher dimensional spaces, or the singularity at the beginning might not be a true singularity, but rather a transition from a higher dimensional state. Some theories propose that our entire universe is a 3-dimensional brain floating in a higher dimensional space, and that the Big Bang was the result of collisions or interactions between such brains. These ideas are highly speculative and remain unproven, but they open fascinating possibilities. If true, the universe's origin might be even stranger and more wondrous than the Big Bang model currently suggests, with hidden dimensions and unseen realms playing crucial roles. The Planck satellite provided the most detailed map of the early universe. Launched by the European Space Agency in 2009, the Planck satellite was designed to measure the cosmic microwave background with the highest precision ever achieved. Over its mission, Planck mapped the entire sky in multiple wavelengths, capturing the tiny temperature variations in the CMB with extraordinary detail. The resulting images are some of the most important scientific data ever collected, providing measurements of the universe's age, composition, and geometry to unprecedented accuracy. Planck's data confirm the standard cosmological model, showing that the universe is 13.8 billion years old, composed of about 5% normal matter, 27% dark matter, and 68% dark energy. It also detected subtle patterns in the CMB that provide clues about inflation and the physics of the early universe. The Planck satellite's findings represent the culmination of decades of work in cosmology, turning the Big Bang theory from a rough sketch into a finely detailed portrait of the universe's history and structure. Cosmic inflation may have created multiple universes. One intriguing consequence of inflation theory is that it might not have stopped everywhere at the same time. In a scenario called eternal inflation, different regions of space stop inflating at different times, each forming a separate bubble universe. Our universe would be just one such bubble. Each bubble could have different physical constants, different laws of physics, and different properties. This idea leads to the concept of the multiverse, a vast ensemble of universes, possibly infinite in number, each with its own history and characteristics. If the multiverse is real, then the fine-tuning of our universe's constants might be explained by selection. We exist in a universe where the constants allow for life because we couldn't exist in any other kind. This is a profound and controversial idea, as other universes, if they exist, might be forever beyond our ability to observe or test. The concept pushes the boundaries of science and philosophy, raising questions about what is knowable and what lies beyond the limits of empirical investigation. We can observe the universe's history by looking at objects at different distances. One of the remarkable features of astronomy is that looking farther into space is the same as looking back in time. Light travels at a finite speed, so when we observe a distant galaxy, we see it not as it is now, but as it was when the light left it. A galaxy 10 billion light-years away appears as it was 10 billion years ago, when the universe was much younger. By observing objects at various distances, astronomers can piece together the history of the universe from the present day all the way back to the first galaxies. This technique allows scientists to study how galaxies evolved, how star formation rates changed over time, and how the universe's expansion has accelerated. The deeper we look, the farther back we see, until we reach the cosmic microwave background, the oldest light we can observe. In this way, the universe itself is a time machine, preserving its past in the light traveling through space, waiting to be observed and understood. Dark energy might be a property of space itself. Dark energy is one of the biggest mysteries in science. We know it exists because we observe the universe's expansion accelerating, but we don't know what it is. One leading candidate is the cosmological constant, an idea originally proposed by Einstein. In this view, dark energy is a property of space itself, a constant energy density that doesn't change as the universe expands. As space grows, more dark energy appears, because each cubic meter of space carries the same amount of energy. This would mean that empty space has an inherent energy, a sort of springiness that pushes against gravity's pull. Another possibility is that dark energy is a dynamic field called quintessence, which changes over time. If dark energy is growing stronger, the universe's expansion could accelerate indefinitely, perhaps ending in a big rip where space expands so violently that atoms are torn apart. Understanding dark energy is crucial for predicting the universe's fate and may require new physics beyond our current theories. Some scientists search for evidence of the Big Bang in gravitational wave observatories. Gravitational wave observatories like LIGO and Virgo have opened a new window on the universe by detecting ripples in space-time caused by colliding black holes and neutron stars. But scientists hope these observatories, or future ones, might also detect gravitational waves from the Big Bang itself. Primordial gravitational waves, produced during cosmic inflation, would carry information about the universe's first moments. Detecting them would be incredibly difficult because they're so faint, but if successful, it would provide direct evidence for inflation and allow us to probe physics at energy scales far beyond what particle accelerators can reach. Some experiments are also searching for imprints of these waves in the polarization of the cosmic microwave background. Finding primordial gravitational waves would be one of the greatest discoveries in physics, opening a new era in our understanding of the universe's origin. It would connect the very small quantum fluctuations to the very large, the expansion of the cosmos, and reveal the dynamics of the earliest moments of time. The anthropic principle suggests we observe a universe compatible with our existence. The anthropic principle is a philosophical idea that addresses the question of why the universe seems so finely tuned for life. The weak anthropic principle states that we should not be surprised that the universe appears fine-tuned, because if it weren't, we wouldn't be here to observe it. In other words, we can only exist in a universe where the conditions allow for our existence. So of course, we find ourselves in such a universe. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some point. This principle is controversial because it seems to blur the line between observation and explanation. Some scientists find it useful, especially in the context of the multiverse, where countless universes exist with different properties, and we naturally find ourselves in one that allows for observers. Others criticize it as unscientific, since it doesn't make testable predictions. Regardless, the anthropic principle raises deep questions about the relationship between the universe and the life within it. The cosmic distance ladder helps us measure how far away galaxies are. Determining the distances to galaxies is one of the fundamental challenges in astronomy, and it requires a technique called the cosmic distance ladder. This method involves a series of steps, each building on the previous one. First, astronomers measure distances to nearby stars using parallax, the apparent shift in position as Earth orbits the Sun. Next, they calibrate the brightness of certain stars, like Cepheid variables, whose luminosity varies predictably. By observing these stars in nearby galaxies, astronomers can estimate those galaxies' distances. For even farther galaxies, they use type Ie supernovae, which have a standard brightness, as markers. Each rung of the ladder extends our reach farther into space. Ultimately, these measurements allow scientists to determine the Hubble constant, the rate of the universe's expansion. The cosmic distance ladder is crucial for understanding the scale of the universe and testing the predictions of the Big Bang model. Errors at any rung can propagate through the ladder, which is one reason the Hubble constant remains somewhat uncertain. The universe's large-scale structure resembles a cosmic web when astronomers map the positions of galaxies across vast regions of space. A striking pattern emerges. Galaxies are not uniformly distributed. Instead, they cluster along filaments and sheets, forming a structure that resembles a cosmic web. These filaments, made of dark matter and gas, stretch across hundreds of millions of light years, connecting massive galaxy clusters. Between the filaments are enormous voids, nearly empty regions where few galaxies exist. This web-like structure is a direct result of the tiny density fluctuations in the early universe. Regions that were slightly denser attracted more matter, growing over billions of years into the filaments and clusters we see today. The voids formed where matter was less dense, as gravity pulled material away toward the denser regions. The cosmic web is one of the largest structures in the universe, and studying it helps cosmologists understand how matter clumped together after the Big Bang, and how dark matter shaped the universe's architecture. Simulation and observation increasingly align in on the universe's evolution. One of the powerful tools in modern cosmology is computer simulation. By inputting the known laws of physics and the initial conditions from the early universe, scientists can simulate how the cosmos evolves over billions of years. These simulations track the behavior of dark matter, the formation of galaxies, the growth of large-scale structure, and more. Remarkably, when these simulations are compared to real observations, such as galaxy surveys and maps of the cosmic microwave background, they match extremely well. This agreement gives scientists confidence that we understand the broad outlines of cosmic evolution. Simulations have also predicted features later confirmed by observation, like the cosmic web and the sizes and shapes of galaxy clusters. They allow researchers to test different scenarios, such as varying the amount of dark matter or the strength of dark energy, to see how the universe would differ. By combining observations with simulations, cosmologists are building a coherent, detailed story of how the universe grew from a nearly uniform beginning to the rich, complex structure we observe today. The Big Bang Theory doesn't explain everything, and that's okay. Despite its success, the Big Bang Theory leaves many questions unanswered. What caused the Big Bang? What happened during the Planck epoch? Why is there more matter than antimatter? What is dark matter made of? What is dark energy? Why are the fundamental constants fine-tuned? These are profound mysteries, and the Big Bang model doesn't pretend to answer them all. Science is a process of building knowledge step by step, and the Big Bang Theory represents our best current understanding of the universe's origin and evolution. It's supported by a wealth of evidence, from the cosmic microwave background to the abundance of light elements to the expansion of the universe. But it's also incomplete, and that's not a weakness, it's an opportunity. Every unanswered question is a doorway to new discoveries, new theories, and deeper understanding. The gaps in our knowledge are what drive science forward, inspiring new experiments, new observations, and new ideas. The Big Bang is not the end of the story. It's the beginning of our quest to understand the cosmos. Time itself may have properties we don't yet understand. We experience time as a one-way flow, moving steadily from past to future. But in the equations of physics, time is often treated as just another dimension, similar to the 3 dimensions of space. Einstein's theory of relativity shows that time is relative, flowing at different rates depending on gravity and motion. Near a black hole, time slows down. At the speed of light, time stops. This raises deep questions about the nature of time, especially in the context of the Big Bang. If time began with the Big Bang, what does that mean? Can time have a beginning? Some theories suggest time might be emergent, arising from more fundamental processes, rather than being a fundamental entity itself. Others propose that time might loop, branch, or exist in multiple dimensions. Quantum mechanics adds further complications, with phenomena like entanglement seeming to defy our usual notions of cause and effect. Understanding time is one of the deepest challenges in physics, and fully grasping the Big Bang may require rethinking what time is at its core. The universe's uniformity on large scales is called the cosmological principle. When astronomers look at the universe on the largest scales, hundreds of millions of light years or more, they find that it looks roughly the same in all directions. Galaxies and galaxy clusters are distributed evenly, with no preferred direction or location. This observation is the basis of the cosmological principle, which states that the universe is homogeneous, the same everywhere, and isotropic, the same in all directions, on large scales. This principle underpins the Big Bang model and simplifies the equations of general relativity, allowing cosmologists to make predictions about the universe's evolution. However, the cosmological principle is an assumption, not a proven fact. Recent observations, such as unexpectedly large structures and possible alignments in the cosmic microwave background, have raised questions about whether the universe is truly as uniform as we thought. If the principle breaks down, it could indicate new physics or require modifications to our models. For now, though, the cosmological principle remains a cornerstone of modern cosmology. You are witnessing the universe at a special time. The universe is nearly 14 billion years old, and it will likely continue to exist for trillions of years. Stars will keep forming for billions more years, though at a gradually declining rate. Eventually, the last stars will burn out, galaxies will drift apart beyond the reach of each other's light, and the cosmos will become a cold, dark, empty expanse. But right now, at this moment in cosmic history, the universe is alive. Stars shine, galaxies collide, planets form, and life evolves. We exist at a time when the night sky is filled with galaxies, when the cosmic microwave background is still detectable, and when the stars are numerous enough to illuminate the darkness. In the far future, beings that might exist will see a vastly different universe, one where the evidence of the Big Bang has faded and the stars have gone out. We are fortunate to live in an era when the universe's history is still written in the sky, when we can look up and see the light from the beginning, and when we have the tools and knowledge to understand our origins. This is the universe's golden age, and we are here to witness it. Time tends well. The Big Bang is both a scientific theory and a source of wonder. Science explains the mechanisms of the universe, the how and the when. It tells us that the universe began in a hot, dense state and has been expanding for nearly 14 billion years. It describes the formation of atoms, stars, and galaxies, the cooling of space, and the stretching of light. But beyond the facts and equations, the Big Bang is also a story of transformation, from simplicity to complexity, from uniformity to diversity, from a featureless sea of energy to a cosmos filled with structure, beauty, and life. It's a story that connects us to the farthest galaxies and the earliest moments of time. Every breath you take, every thought you have, is part of this story. The atoms in your body were forged in stars. The space around you was once part of the singularity. The light you see is the ancient glow of creation, stretched and cooled but still present. The Big Bang is not just a theory. It's a reminder that we are part of something vast and ancient, something that began long before us and will continue long after. And in that realization, there is both humility and wonder. Thank you for spending this time here, drifting through the origins of everything. We've traveled from the first instant of the Big Bang, through the formation of atoms and stars, to the present day, where we find ourselves gazing back at our own beginning. Along the way, we've encountered mysteries and marvels, questions we can answer, and questions we're still pondering. And somewhere in all of it, in the light of the cosmic microwave background, in the expansion of space, in the atoms that make up your body, there was you, breathing slowly, thoughts softening, maybe already asleep. This universe is full of motion and mystery, but also stillness. It holds heat and light and gravity, but it also holds peace. And the fact that we can know it, piece by piece, in calm and in quiet, is something truly beautiful. So, wherever you are now, whether you're fully awake or drifting beyond the edge of thought, may your dream tonight be gentle. May your body rest like starlight on water, and may you carry with you, even faintly, the memory of a universe that began in fire and now holds you here, softly, in its vast and ancient arms. If you happen to still be awake, you can go ahead and watch the next chapter now. And if you'd like to drift off to more stories like this, softly told, filled with wonder, consider subscribing. There's always more to explore, one sleepy soul at a time. Good night.